estábamos dándole tiempo a más gente que viniera, pero yo creo que ya, por respeto a los que llegaron a tiempo, podemos empezar. Bueno, de parte de la unidad de puentes del programa de Ingeniería Estructural de la LanammeUCR de la Universidad de Costa Rica, muchas gracias por asistir. El tema que le tenemos es el de fractura y fatiga en estructuras metálicas, dado por el profesor Mathias. Él nos acompaña desde la Universidad Técnica de Múnich. Es parte del Departamento de Estructuras Metálicas de la Escuela de Ingeniería Civil de esa universidad. Él es docente en esa universidad. Él da los cursos entre varios, de fatiga y fractura, de análisis mediante computadora de estructuras de acero y compuestas, el curso avanzado de construcción en estructuras metálicas, entre otros. Por supuesto, entre sus varios énfasis de investigación está el análisis de fractura y fatiga en estructuras metálicas. Creemos en el programa de ingeniería estructural, que es un tema que ha sido poco abordado, no solo en la práctica, sino también de parte de la docencia. Hay ahí un gap en la enseñanza de lo que es fatiga y fractura. Si bien es cierto en el caso, digamos que en el caso común de los edificios no es un tema tan común, pero ya cuando hablamos de estructuras livianas sometidas a cargas dinámicas de viento y principalmente en el caso específico de puentes, pues el análisis de fatiga se vuelve pues un caso bastante importante, y en donde a nivel mundial se han dado fallas de puentes bastante grandes debido a este fenómeno. Él tiene experiencia en varias también compañías alemanas, en el caso de construcción de edificaciones, principalmente de acero, y en la construcción de puentes, también en el caso específico de acero. Entonces, los dejamos con el profesor Mathias. Van a ser 4 mañanas, como ya saben, esta mañana, el jueves, el lunes y el martes de la otra semana. Así que, bueno, ojalá nos puedan acompañar todas estas mañanas y podamos aprender un poco de este interesante tema. Muchas gracias.
So, hello everybody. My name is, as Esteban already mentioned, Mathias, and I'm a PhD student from the Technical University in Munich. And I welcome you to the 4-day program to fatigue analysis and fracture analysis in metal structures. So I'm from the Technical University of Munich, and there I work at the chair of metal structures of Professor Menzinger. So here is Munich and here is San Jose. So I had a short trip behind me. And also thank you to be here and to arrange this program, and to do here a little bit more on this topic. So this is our chair of metal structure. This is our professor Martin Menzinger, who allowed me to come here. And just to give a short overview of our topics, what we are doing at our department or our chair is, at first there are some guys who are working on blast analysis, so they are just design and numerical simulations, no experimental investigations. Then we have a topic on the buckling analysis of bridge girders and composite structures under fire loading, fatigue analysis of joints with aluminum alloys and steel or steel, and also fracture analysis of steel, especially here for rail systems. Regarding the railways, if they're gonna brittle in summer or winter or in spring, so to enhance the system and the durability of the railway system in Germany. So, what I will do the next days is, as I talk to Esteban, that we are doing in the morning some introduction always to one topic, so more theoretical. And in the second session, I would go for an example, and there I would work on this example. So for today, we have the topic Introduction to the Fatigue Analysis. And therefore, I'm gonna start here with the basic historical approaches and also what is behind the fatigue and fracture in a material as steel or aluminum alloys, which are at the first point for engineers always a really homogeneous material with no really defects, with isotropic material behavior, and so on. So what I hope I can give you today is at first the economic importance of fatigue, but here also in point of view on, I would say, European industry, because until now I do not know so much about the Costa Rican industry and the transportation system there. Then we learn about the fatigue problems which occur in civil engineering practice. Then also how fatigue is defined. So what are the specific parameters, what are the specific names we have to learn, and what are the first ideas for the fatigue correct occurrency, and also some basic procedure for a design of structure against fracture. Structures against fracture, sorry. So, so what does fatigue mean? So the fatigue, as you can see here, is always referred to a time series, a stress time series, which is quite variable. So in basic assumptions, as in testing, we always go there with a sinus, and but the reality always has something like this. So we have here a strain, a stress or a strain, and this stress or strain varies during time. So due to the fatigue, the material loses resistance due to the frequently changing load. So therefore, we have relevant fatigue stresses. So they are somehow the peaks from here to here by the range of the stress and the number of cycles. So in the next one, there are some parameters or some, I would say, environmental or effects which can also act on our fatigue behavior. And this fatigue behavior is the load sequence. So as here, do we have some high peak and some low peak, and again some high peak, and afterwards some low and high and low peak. And due to the arrangement of the situations of the high peaks and the lower peaks, there can be some effects on the material. So then also the local stresses. So how is the constructive design of the structure? How is the building designed or the structure designed? Then also some production factors which are more related to welded parts and screws and so on. And then the next part also, which we usually as engineers always do not have in mind, are the imperfections. So usually we always talk about some idealized beams and plate systems. But due to some second stress effects due to the welded part or due to the joints, we have there some influences due to the imperfections. And then also the environmental conditions and material properties. So usually in fatigue analysis regarding to civil engineers, we usually say, okay, in European standard that we do not work in maritime area. So because the maritime area, due to the salty water, has much more corrosion, and therefore you have to conduct more specific testing, which are usually not important for the civil engineering structures in this case. So the fatigue historic in Europe, as I mentioned here, is that the first observed and documentation of fatigue damages were by William Albert at 1829. So now we have around 180 years of knowing this effect. And then at first around 10 years later by Ponsner-Metz. The word fatigue was established, and he established it due to the behavior of persons. So if a person is getting tired, he also has some fatigue problem, and so this he mentioned that also the material gets tired, and so he mentioned or he established the word fatigue in this situation. And at this time in Europe, we had the investigation of the Industrial Revolution, and so there have been a lot of train systems established. And due to this, the first real problems appeared at train huge, particularly on the axis. And as you think about, okay, if you have a train, the axis always rotates, the train system is not as perfect straight, and so you get there a lot of different cycling loading. And due to this, there also the first real problems appeared. And so 20 years later, Mr. Wöhler, he also was interested in this topic, and he was running a material testing laboratory. And so he investigated the first testing procedure to define some resistance curves, and this is also today also now well-known Wöhler testing or fatigue testing procedure, which was established 1840, and in this time, always getting some improvement, but the thinking behind is always still the same. So, what are the problems we have due to fatigue is, of course, our notches. So, as I already said before, we have different structures, and the stress increasement always leads to higher stresses in the microstructure of our material. So, and for example, if we have like something like here, a notch like this, which is very sharp, or a notch which is somehow more smooth, also the stresses in the ground of the notches are different. So, and due to this, the notches and also the constructive design of the notches have a great influence on the fatigue, because as you can see here already on the tension lines or on the vector lines of our stresses, at this point we always get the higher stresses, and also if there are the cyclic loading, the stress ranges may be here at this point the highest. So also the next one is some irregularities in wells which are also acting on our notches. So for example, here are some specific details we usually classify our problems. So for example, we have here a steel plate, and this steel plate we have here some welded part. Due to the welded part and the notches here, we have at this point a stress increasement, and so at this point also some fracture and some crack appears and gonna start, and at the end at this point our structure or our beam can fail. So the next one is here on a smooth tension bar, maybe, where we join some different bars with different thicknesses. So we have at this point we have increasement of the stresses from this point to this point. Due to this, also the stresses at this point are also increasing. So at this point we get also some crack occurrence, and at the end somehow our structure fails. So how does it look like? So this, for example, is a section which looks like this. So some hollow section, and we are now looking at these points. And so here our fracture occurs. So, and here we can see that due to our welded part, we have the welded part here, and at the root, weld toe of our weld seam, we have here our crack occurrence, also due to the notches which are here at this part. And so, as we can see here, the weld seam itself is not really large, but already we can here see our cracks. And this is something which can be tested due to NDT testing procedures. But at the end, you can already see such a crack by a size of 0.5 millimeters. If you are really into looking at the right positions, and so you already can see, okay, where a crack might be, and then how large can be the crack or somehow else. So, and for a typical structure, so for example, for a bridge like this, we have here our tension bars, and at the bottom point of our tension bars, we have here the connection. And as you can see here, due to the stiffeners at this point, and this point, at the end of the stiffener, our crack occurs, because also here, as I also before mentioned, the stress behavior and the stress state at this point gets some increasement, and due to this, at this part, our cracks gonna appear. So, what are some specific parameters in a welded construction? So here we say about the weld imperfections, but also at this point we have a little bit to divide between weld imperfections inside the weld and weld imperfections acting on the joint. So weld imperfections acting on the joint as a stress increasement would be a misalignment like angular or axial misalignment. So this means like we have here a joint, and this would be an axial misalignment. And this would be an angular misalignment. So this is something I'm going to go specifically tomorrow at this two effects which appear there. But today, at first, we just look inside the material, and so we are talking about the notches inside the welds and also the weld imperfections. So here you have a short drawing. So this is, for example, a butt weld, and there are some effects which are, I have here both naming, so in German and in English, due to the lecture we give in German. So we have at this point, we have a lack of fusion. So as you can see here, at this point, there is a loss of material. So there is no joint between the base material and the weld material. And the next one is here some inclusions. So some, as in German called Anschlüsse. And the inclusions are some material which is really bad, in a really bad condition, which may occur due to the welding process, due to some bad welding parts. The next one are also the slags, which can also appear next to the lack of fusion, and also some brittle surface layer. So this brittle surface layer can occur at this part, and also in this part. This means usually we design or we choose our materials due to a ductile behavior. And so if the material is not really ductile at this part, it can, there are happening more deformations in the microstructure. And due to this, the brittle structure has a faster crack initiation. And so at this point, due to the brittle structure, the crack appears much more earlier. And so these are some weld imperfections which can cure during the welding, and which also has to be carried due to the NDT. So if you go later and test your welded parts, you have to look that there are no parts like this. So how does it look like? So for example, these are some pictures of an X-ray. And here you can see, for example, in the weld imperfections, some root defects. So a root defect means at this part we have here the butt weld, which is a V-seam. So the V-seam is welded from one side. We have here a weld preparation. And at this part, the welded part is not completely welded. And so the crack gonna start at this point into the material, and at the end also the structure fails. How does it look like in our X-ray? The X-ray at this part here, you can see it's perfectly done. And this line shows you, okay, there is some root defect, and this root defect, you have to do again and start again your welded. So open the welding again and weld again. So what is the slack inclusion? So also, as you can see here, before we said, okay, the slack inclusion is some failure in the welded part. So also here, the slack inclusion appeared next to this part and next to this part. So always the black parts, there is some mistake in our weld seam. And then the next one, localized porosity. So a porous welded part is also, you have some pores, and the pores are also the starting point of the cracks in the structure. And due to this, in the X-ray, you can also see, okay, how big are the pores, how many pores are there, and what are the amount of pores. And so you can say, okay, does your welded part or your weld seam satisfy your quality management or also your quality regulations? So where can it appear? Just some introduction again. What are we talking about? So of course in wind farms or offshore wind farms, we have a high amount of cyclic loading due to the wind turbine here. It is rotating, the wind has some turbulences, and also the water, it is rough, and so at the end we have here a lot of cyclic loading, which are really changing a lot. So due to this, here we have some analysis we have to do. There are just some drawings how it looks like, and how such a analysis gonna be done in the industry. So here we have the top point, which is this part here. This part here is analyzed by a 3D model, and at the end you're gonna see, okay, how much loaded are your static design, but also your static fatigue design. And this is also something I'm gonna go in a more smaller part tomorrow. And also for the crane and spreaders, the same machine. So you have here the crane structure. The crane structure is always lifting some loading, and due to the lifting, you have a high amount of cycles, which can be really huge. And due to this, also the structure is really loaded by, or has really fatigue problems. So, of course, marine diesel engines. So which stages of fatigue processes can appear? So the fatigue process, usually you talk about the crack initiation and the crack growth and the residual fracture. So these are the three main parts. The crack initiation is usually done by the structural changes of damages exclusively on microscale. So here we're really talking about microscale material defects and so on. And the next one is the slip bands, which occur mostly in the planes of the maximum shear stresses. So this is something, if you're testing, for example, steel bars in laboratory in the tension test, you also can see the slip bands. And also the impoundment of dislocations at the material surface, so the development of peaks and valleys. And also along the slip band, micro cracks occurs. So here you can see you have some defects in the micro scale area, and due to the loading which occurs to the slip band, also the deformation starts, and this deformations the micro crack starts, and so this is the initiation of the crack. Then our crack starts to grow when the microcrack reaches distances which is approximately the grain size. So due to the materials, usually you have different grain sizes. So at this level you cannot say, okay, the crack growth starts at this. Usually you say, okay, you're talking about long cracks if the crack has a distance of 0.2 millimeters, 0.5 millimeters, because then you also can see this crack in the inspection. But before, there is no issue that you can see it, and so this level also is somehow related on the crack size or on the size of the grains, because then the first slip between the grains is broken and or already cracked, and the crack growth started. So, and at this level, so you have the first grains which are broken, and so at the end, some different cracks may combine with other microcracks and then start to a microcrack. And the microcrack is what I said before, is at the end the crack, the long crack, which you can obviously see in some inspection, and which you at that level also can talk and go for some enhanced investigations. So the residual fracture is the growth of the crack, and also at this point the reduction of the cross section. So what happens is we have here our crack, for example, with this loading. Usually in your static design you would mention sigma n, so the nominal stress is F over A, and our crack at this part is going into the structure, so you have here some reduced section, and so also the nominal stresses, and at the end your static design also is influenced on the crack occurrence. So, and in some later section or the stadium, you have an unstable crack growth. So this means that the crack grows faster, and your structure or this part here will fail rapidly. So, and this is also something usually we are at this part talking about ductile and brittle fracture, and this is something which is tried, I would say, which is in the codes tried to investigate to find a solution of the maximum crack length at which the crack at the end goes to a failure of the structure, so that the engineers can say, okay, at which part is the maximum level of your crack occurrence, and that at this part yeah, you have to change your structure, you have to maintain your structure, or to find another solution. So, what is the stages of the fatigue process, which I already mentioned here, is so we have stress cycles, and due to the stress cycles, there occur some local plastic strains. So, and these local plastic strains are related to some microcracks form to main cracks. So this is the combination of the microcracks due to some larger cracks. Then, as I already said, we have some development of cracks, then the reduction of area, and at the end, the failure. So in the material itself, it looks like this. So we have some slip bands, which you can see here at this part. So this is just some local deformation of our material. Then we get some microstructure, which you can at some parts see here and there. Then we get some main cracks, which are here in this part. And at the end, we have a macro crack, which is quite huge and has here the crack tip, which we're going to talk tomorrow. So then, what are the stages of the fatigue process again, but on the view on what I can obviously see on the specimen I tested in the laboratory. So the testing in the laboratory usually looks like this. So this is a round bore, which is just done due to a normal fatigue testing with the sinus loading. And you can see here at this part the crack initiation. So this is a small part. You have here some local deformations or some failure in the material. And at this part, due to the failure in the material, you get the first cracks. And at the end, you have some crack propagation. So, and the crack propagation has some smooth and fine, sometimes porous crooked zones of fatigue fracture. And this zone, at the end, you can see here some line of rests. So these are always the more, I would say, darker lines. And this part, so you have the sinusoidal loading, but still the crack occurrence or the crack propagation is not continuously. So you always have some lines where the grain structure has some resistance. So at this part, you have some line of rests, as we say. So the crack is not growing not as fast. And afterwards, if this resistance is going to broken again, the crack propagation starts again, and also some rest line occurred again. And as you can see here, also the surface here is quite smooth and looks quite fine. And at the end, you have some first fracture. So the first fracture is at the end also the fracture of the round bore. And this is more like hilly, more like a mountain structure. How does it look like in the microscope? So in the microscope, you can see here, this is the crack propagation, and with some small lines. So this is the crack propagation, as you can see here. And the first fracture is the more hilly part. So this is really the part where at the end the structure fails, and also the coarse grain is gonna brittle. So again, some smaller parts of not of a round bore, here of a rectangular cross section in a welded part. So here you can see the weldment is on this part. This is at this level, you can see the weld toe. So at the weld toe of this small specimen, you have at the whole side the crack initiation. But due to the curves, you can see, that the crack initiation was somehow more on this side than on this side. And due to this, you also see the marking cycling, so the rest lines, and the main cycles, which are the crack propagation. So, and this is usually how it looks like, and then some stable crack growth. So how our crack is going from the specimen from the outside. So here, this is the border, the surface of our specimen, and of course the crack grows from this part into our specimen. And here you can see, okay, this crack is not straight. It always is some lines, but the crack is moving due to the grain structure and due to the microscale system inside the material. So then a more theoretic part to know about, okay, what is the problem in the microstructures due to the crack initiation. So the crack initiation is always something of the, I would say, a more material related part, and which is for engineers not as interesting or not as important, but we have to know about the problems there, and also about some effects which are related to this problem, to have also the quality procedure in our structures, or due to our processing, where we establish our structure, where we do our welding parts, where we fit our screws, and so on. So what is the main idea here? The main idea is at first how gonna crack appears. Then also the difference between the brittle fracture and the sliding fracture. So, and the next one is the effect of local plasticity and the cycling stress-strain relationship. So this means at which part in our material do we have a cyclic stress-strain relationship, which also influences our material behavior, and at the end has some influence on our structural, or on the initiation of the cracks. And the last part, which we're gonna focus here, is the mean stress influence on the fatigue. So just a short view, what is the mean stress and how is the mean stress related to different materials. So the fatigue of metal structures. I think everybody knows about our paperclip effect. So usually if you're sitting at the chair or somewhere in the office, you're thinking and you're gonna play with the paperclip, and during your playing with the paperclip, usually somehow it's gonna phase in two parts, and this is, I think, the fatigue problem everybody knows from daily life. And in our structure or in the material, there is in some related part the same effect happening. And so we have there a cyclic varying stress, and after a finite number, so this is the numbers you're gonna twist around, the paperclip somehow fails. And this is the so-called fatigue fracture. And of course, in this situation, we have a really ductile material, and so this ductile material also gets a lot of plastic deformation, and this plastic deformation is always really local. So, for example, in this part, this local plasticity occurs somewhere here, and so due to this, at this local part which get or is influenced by the plastic deformation, at the end the crack occurs. So what is the fatigue loading? The fatigue loading, an engineering part, is somehow a little bit different, because we do not obviously induce plastic deformations in our structure. So we have here our stress-strain curve of a metal sheet, for example, and so we have here our yielding strengths and here are the ultimate strengths. So, and the cyclic loading, which we're talking about here in fatigue design, is always beyond the yielding pass. But due to the numbers of cycling, which we apply on the structure, also the crack gonna appear. And so we have some endurance problem at the end, which occurs due to the size of the loading, so of our stress range, and also due to the numbers of cycles we're gonna apply on our structure. So at this part, I just want to introduce the main words or topics we have to think about the fatigue loading. So the load cycle is always the part from the mean value and the sinus to the mean value. So this is one cycle. So what is the minimum stress? The minimum stress is always the lowest peak of one cycle. The maximum stress is the highest peak of our cycle. The mean value, of course, is the mean value of maximum to minimum peak. And the stress range is at last is the difference between the maximum stress to the minimum stress. So, and then we have to introduce the stress ratio, because the stress ratio at the end is always the parameter we are talking about in fatigue design. So there we do not talk about the mean value. We talk about the stress ratio, because the stress ratio is giving more information on the behavior due to the structure and due to the loading which occurs due to eigen death weights and so on. So, and the stress ratio is always defined as the minimum value due to the maximum value. So, this is the box we're talking about inside the fatigue design. If you now go to the microscopic background of our material or of fracture, we always think about some repulsion and also attraction of the atoms and of the nucleus. So at this part, the fracture is always a separation of the material. So the material is always done by some atoms, and at the end also of the nucleons, which are positive or negative. And so the repulsion is always the electromagnetic force between the two positive nucleation, and the attraction is always the electromagnetic binding between the two atoms. And if the fracture occurs, this is what's gonna be here is that we have a force which at the end is related to the binding force, and the binding force is related to the atomic radius. So this is Rm, and due to the Rm we can formulate, due to the distances of the atoms, a fracture specific material work which is related to the fracture occurrence. And this is somehow the schematic drawing which is shown here. So we have here somehow the atomic radius, and with the higher distance of the atomic radius, also the attraction force is reduced and also the repulsive force is reduced. So, and at this part, if you now go into the structure, we have always small dislocations. So dislocations in the atomic structure means that there is a part which is not in the regular size or in the regular order. And due to this, we have a dislocation T0, which leads to a approximately linear behavior. So this is always the background we are talking about in the fracture of the microstructure. So how does it look like? So due to the fact that fracture only influences the crystal lattice, close to the new surface, the work of the binding forces Vb can be interpreted as a surface energy. So this is a nice sentence, which we always have to a little bit more combine for the students. So, for example, we have here our stresses, and the stress is always acting on our microstructure. So these is the stresses which are also working on the dislocations and also working on the attraction of the atoms. And due to the fracture, we have a crystal lattice, and this crystal lattice is always, as we say, new to the new surface. So this means if the crack occurs, some atomic binding breaks, and at the end we have here a new surface, and due to the new surface we have a new fracture energy which is related to the situation. And this can be formulated by these nice formulas. And at the end, due to the Hooke's law, which is some law which is always working in engineering sentence for linear elastic behavior, we can formulate our sigma c, and due to the sigma c, also we can formulate a fracture energy which is related to the atomic structure. So, and for this we have some specific values, and at the end, due to, as we know already, the modulus of elasticity is about the 10.1, 10/5 MPa. Then we can measure in laboratories the distance between the atomic, and this is defined here to 2.5/10⁻10 meters. And we also get here a sigma c, which is related to the binding force between the two atoms, and a stress value which is showing the work between the atoms, and therefore we can at the end formulate energy formulation, and this energy formulation leads to the work we can apply on our microstructure. So this is somehow I would say the smallest theory which is related to the occurrence of crack initiation in the microstructure. And but as you can see here, this model which you see here is some model which we are also using for large scales. So for example, if we think about a plate, and at the plate we have somehow here a failure, and this failure at the end grows to both sides. We also use the model with the plate and the crack through the plate, and this is a model which also works for the small microstructure. So at this side we can go and say, okay, which defects of polycrystal material we're going to talk about. So these are the regulatories of material in mesoscale. So we have some polycrystalline material, and this polycrystalline material consists at the crystal boundary connected to the crystal. And also the orientation of the crystals in the space is irregular and causes some anisotropic behavior in the material. But at the end, for the engineers or in engineering behavior, we always talk about an isotropic material. So this is something which is really related to the microstructure. And at the crystal boundaries, some excretions can be found. So this means that due to the loading of the microstructure, also a change in the atomic order or in the microstructure occurs, which at the end has some influence on the crack initiation and also on the crack growth. So this is more, I would say, more related to the material behavior in the structure, and there's also more interest in the material science. And also the cavities and the microstructure from fabrication exists, of course. So the next point I'm gonna skip because this is more explained on the next slide. So this means the importance of dislocations. As we before said already, we have a linear dislocations, sorry. And the dislocation always means that we have here, at this part, we have a perfect structure of our atomic girder. And so this is how we think usually about some metal structure, some aluminum alloys. But of course, at some parts, there are always some failures in the microstructure, and these failures are called the dislocations. And these dislocations can be, as here, some linear dislocations. So this means that we have here a failure in the structure, and at the end, this line is gonna be skipped, and this line is combined by this one. And then also the screw dislocation, so that we have here some part which has no connection, and at the end, it's gonna be done like a screwing, so like a torsion on the structure, and this can be also some dislocation which appears in your regular material. And and under shear, or also due to the normal stresses, I would say, due to the normal stresses, this dislocations leads to a new arrangement of the atoms, and therefore also to a shift of the dislocation inside the microstructure. So, and at this point, we always have some loss of energy because, as we saw before looked on the microstructure, this theoretical model is always working like on a perfect model. So, and this perfect model, of course, does not work here. So we have here already some loss of our theoretical model inside the material. And therefore, of course, due to the loss of the surface energy, we also get some new surfaces inside the microstructure due to the crack occurrence, or due to the microcracks. And this also, as I said before, leads to a mechanism, to a well-known macroscopic plastic material behavior at a monotonic loading. So, and this behavior of the dislocations and also of the rearrangement of the slip bands is so-called, or we also know from the tension test, and this is the concentrator is so-called the slip bands, which are also known as the Lüders-Bänder. So the Lüders-Bänder is something, if you, for example, go in laboratory, do a testing in a tension test for steel boron, you also can see these Lüders-Bänders because they are always somehow in a ductile material in an angle of 45 degrees due to their tension force. And so at this part, this Lüders-Bänders acts as the shear forces which are acting on the dislocations. So hopefully no. This is just, I'm gonna show later, this is a small movie of a tension test where you can see how the Lüders-Bänders appear and how it's gonna be built in the material. So now I got this some small introduction just to get into the thinking of what is gonna be appear in the microstructure. And now we're gonna talk about the development of cracks and also the brittle fracture. So during the deformation process of the polycrystalline materials, some other mechanisms of the microcracking are affecting the crack-free material. So as you see here, you have some cracking in the surface. So, and there, this material cannot handle anymore the stresses. So also the stresses around the material around, which has no stresses, are influenced. And so there are some higher stresses around. So this is something like in the micro scale, the same as we had here already in the macro scale. So, and usually due to different material behavior or due to different material structures, there can appear different cracks. and these cracks are called the transcrystalline cracks or fractures, and these transcrystalline fractures go through the crystallines of the material. And on the other side, there are some intercrystalline fractures, and these intercrystalline fractures are going always on the boundary of our crystallines, and at the end are working different in our structure. So, and therefore, the statement in the case of crack through several grains, the orientation of the crack surface depends on the local orientation of the crystals. So as we can see here, we have here the orientation, and it goes more straight. And at this part, we have not a straight line, so it is more more curvy. And so at this point, also the boundaries and the orientation of the boundaries are more influencing. So how does it look like, a brittle fracture? A brittle fracture looks like a little bit the same as we had before, so as the forced fracture. But at this part, we have some small deformations and just only slight constrictions. So this is something we usually talk about, for example, for low temperatures. So, for example, for low temperatures, the material is not as ductile as, for example, as in normal temperature or high temperature. And due to this, the brittle fracture occurs. And here you also can see in the microscope the difference between the transcrystalline failure and the intercrystalline failure, which here is more smooth again, and here we have a more hilly structure, which we say, okay, crow's feet, so the feet of a bird. So, and this is the development of the cracks. So as I already said before, we have here the interaction of some small cracks which are here. And due to the small cracks, which can be a pore, which can be a defect in the material, we get also some acting on the material around. And this small pore or a defect at the end grows to both sides. And at the end, we get here some combination. And this is how the crack initiation starts. So we always have some small parts which have some material defect. And at the end, we get some bigger cracks. So, and this is if we are now going more to higher loadings. So for example, as I said before, we have a mean value of our stresses, and also the mean value is influencing our crack occurrency. And if you go, for example, to higher stresses, we always have here our slipping bands. So these are our leader spanders. And due to these slipping bands, which occur to the loading, at the end we get here some, I would say, in an easy way, some rough surfaces. And due to the rough surfaces with the peaks and the valley, we at the end have here the currency of the sliding process. And this at the end leads to the extrusion. So this is the extrusion, the peak, and the intrusion at the material or at the surfaces. And so this leads at the end to the surface crack, which can just appear at this side. So, and due to some, I would say, specific task, we were also talking in advance. We have also added here this cyclic stress-strain relationship. So this is something usually you know about the tension test. And in the tension test, you usually have a material behavior like this. So, for example, if we now go for a cyclic material behavior, we usually would say that due to the material laws, our structure is loading and unloading due to the modulus of elasticity. But due to the local plasticity, also some different effects occur. And these defects can be like this. And so we get here so some hysteresis, and the hysteresis are usually the part which you think about if you go for earthquake design. So this is the part which also handles at the end the energy loose in your material or in your structure. So, and this is always related to the cyclic stress-strain relationship, and this cyclic stress-strain relationship is some plastic deformation, and this plastic deformation might be macroscopically visible for the nonlinear stress-strain relationship in the case of cyclic loading. So this also means, okay, that in some behavior we always have here a plastic part and some elastic part. So the elastic part is always going, as I explained here, due to the modulus of elasticity, and the plastic part at the end takes the energy which is applied to the structure, and at the end is also somehow related to a damage in the material. And due to the behavior, so this is related to the material itself. So it can be different for each, for example, for aluminum alloys or for titan alloys, or also for different steel materials. You can have a cyclic softening or a cyclic hardening. And the cyclic softening and the cyclic hardening always means, for example, that at the end for a cyclic softening, in a really easy explanation, you have a loss of your modulus of elasticity. And at the other side of the cyclic hardening, your material gets stiffer due to the cyclic loading. And this is something you also can, which is related to the material, to the microscale structure, and which you also can test in the material due to different testing methods. So how does it look like? So as I said already, so this is your tension test at this site. And for a cyclic hardening, as you see here for the cycles, it gets much more stiffer. So this is the cyclic hardening. And on the other side, you also have here the tension test with, at this part, the wide branch of Lüders-Benders. And also at this part, the material loses on stiffness, and it is a softening effect at the material. And these effects usually appear at the first 1,000 numbers of cycles. And so it's really much more related to high stresses or high applied values of forces due to the structure. So how can you, for example, test this in the laboratory? So this testing procedure is somehow related to the incremental step test. And this is just one, I would say, one procedure out of 3. If you at the end separate on the applying of the loads, on the applying or on the testing procedure, at the end you can talk about 9 different incremental step tests you can conduct on your material. But how is it going to be done? So usually the incremental step test is defined by cyclic loading, which is more looking like a triangle or a rectangular. So you start here at first with the plastic deformation in the tension test, and afterwards you're gonna decrease your loading and increase your loading again, and so on. And due to this, you get a shape of the hysteresis, which look for the whole testing like this. And this here at this part is a material which has no specific cyclic softening or hardening. So because if you would have a cyclic hardening or a cyclic softening, this point here would move, for example, in this direction or in this direction. So at this point we talk about a completely stable cyclic material. And due to this, due to the peaks, you can at the end define the behavior of the material and also the cyclic behavior, and the plastic deformation, which can be handled by your material. And this is more applied to local concepts, where you say, okay, what is the real amount of energy which is in your structure, but also at the same time leads to damage inside your material and inside, for example, your joints. So how does it look like? The influence of the load amplitudes on your cyclic material. So if you're talking about the cyclic stress strain behavior, we always talk about plastic deformations in the material. So the plastic deformations, as you can see here, are much more higher when you apply higher loads. So this is always related to the loading at this side. And also at this side, you're gonna see here the load cycles which you're gonna apply. So as you can see here, due to the loading, the first plastic deformations are always done at this part. And at the end, you have an increasement of the occurrence of the plastic deformation. For the high stress amplitude and for the small stress amplitude, this effect is more in the future, I would say. So as you can see here on the amount of cycles, of course the plastic deformation also occurs due to the change in the microstructure. So this is here a real, I would say, local effect in the microstructure, but also it occurs later. So, and at the finishing part from the material behavior, I would end with the mean stress, and the mean stress is always, as we said before, the influence of the mean stress value, and therefore is also related to the stress ratio, R, which is defined by this value here. And so the mean influence of the mean stress, for example, can be seen here. So for example, for higher loads, for a higher amount of cycles, you also have here some influence on the mean stress. So for example, this is something which occurs due to, in the microscale, due to the plastic deformations. So if you think about your cyclic stress-strain relationship, you get some plastic deformations, and the plastic deformation at the end are some information in the material which is still there. And due to this, you also get here some mean stress information or some mean strain information in the material, which is for here at this part increases with the amount of cycles. Also here, the same part, you can see how it appears. So how is it related to different materials? This is something, because this is some, I would say in this case, more related to the material testing, to the real assumptions if you go for your material. But if you go for a material which is usually defined in context of civil engineering, there are not as many steel steel specifications you're going to use, and also not so many aluminum alloys or different alloys you're going to apply for your structures. So therefore, for example, you have some which is called mean value effect and or influence. And this mean value influence you can see here. So for example, for some material which you're gonna use in, or which we're gonna use for the daily design in Europe, this is the ST37, so, and the ST52, so which has a yield strength of 235 megapascal or 355 megapascal. And so you see here that the mean value effect is really low, but also you can take this influence in your design, which I'm gonna talk tomorrow. And at this part, you have some small influence. This is really low. But for example, if you go for some other alloys like some titanium or gusset materials, the effect much more increases. And yeah, I think this is okay for this. And how does it look like? This is what I meant before. For a stable material, you have no influence. So if, for example, for a not cyclic stable material, which is load controlled, you see here, you always reach the same level of loading, but due to the plastic deformation, you get some effect that the material shifts in this direction, and you get some mean strain information into your material. If you go for a strain-controlled testing, also done by incremental step testing, you always reach here this point of strains, but due to the softening effect, the amount of stress you have in your structure, or which is measured in your load cells, is going to be decreased. So this part was done to get you the information on which effects can occur in the material, which effects are lead on some defects in the material. And now I want to shift from this more material specific informations to our design information. So this is what we call the nominal stress design concept, which is here related to the Eurocode EC 319, but the same concept you can also find in the AASHTO. So this is, in this case, I would say the concept itself is not related to the code, because maybe there is some different assumptions in the resistance curves, but the main thinking and the main concept is going to be still the same. So, and again, the concept itself, how is it, what effects can be handled by the concept. So this information is more like what happens after the correct initiation. So, for example, this is the characteristic length of your crack. And so for the small characteristic length, you have a real damage mechanism, which is more in the microscopic influence structure. And after 1 millimeter, usually you say, okay, this is based more on fracture mechanics. And in the nominal stress concept, you want to apply a concept which is influenced by both parts. And so at the end, if you're going to test due to the nominal stress concept, you're always testing at the end of the fracture or the failing of your beam, of your testing specimen, of your joint. So this is what you're going to test there. And so how is it related to the initiation and also the correct propagation? So for example, if you see here this small specimen, we have here this small specimen, and at this part we have a hole. Of course, as I explained before, at this hole we have the highest amount of stress peaks in the material, and so the crack obviously occurs at this part. So at this part, the crack occurs and leads to a crack growth and crack propagation. And at some situation, at the end, this part fails and the structure or the specimen fails. So how is it related to the amount of cycles and the crack size? So we have here, we have a crack initiation, which is quite long. At the end, we have a not critical crack propagation, so this is a more smooth behavior at this part. And at the end, we have the overcritical crack behavior, at which part also our specimen fails and our specimen is going to be broken. And so this is the crack growth of the appearance of a crack can be described using the methods of fracture mechanics. And this is also something we're going to talk hopefully tomorrow. And in the current standards for the C structures, the nominal stress is used based on fracture SN curves. So this means the amount of cycles we're going to apply there is always the fracture of the specimen, of the bar, of the joint. So, and what is, how is it going to be applied? So we have, as I said already, we have a nominal stress concept. And the nominal stress concept in this case of civil engineering or in context of engineering is always related to a multi-stage load spectrum. So therefore, we're always talking about global stresses, which we are going to use for our calculations. So for example, we go there, we do some analysis on some beam structures, and with this information of the beam structures and the recalculations of the stresses due to the Bernoulli beam, we can estimate our stress ranges, and in the resistance curves of the nominal stress concept, all information, so of local peaks due to some notches, holes, and so on are already applied. And this information is done due to the notch classes, which you can find in the codes. So at this level of the design, we have a quite rural approach. But due to the rural approach, we can also define or get a good amount of estimations, and also leads in an engineering context at the first level of the design to a good approach. Then, due to the multi-stage load spectrum, we have a linear damage hypothesis, which is done by Palmgren Minor. This is something I'm going to show on the next slide. And due to the damage hypothesis, we can also recalculate some equivalent stress amplitude range, which is like we say, okay, we have a different amount of stress ranges. For example, a stress range of 200 MPa and 240 MPa. And this, at the end, due to the damage equivalent stress range, we recalculate a stress amplitude or a stress range which has the same amount of damage inside your structure. And with this information, at the end, we can also give some lifetime prediction due to the stress in the SN curves. So this is the procedure you usually go through for the nominal stress approach. And so again, what informations do we need there? At this side, of course, we also need the stress ranges and also our R, which is defined by the minimum peak to the maximum peak, and also, as I said before, the numbers of cycles. So what is also the dependency of the curves on the mean stress? So, for example, the notch details, so the details we are usually talking in the normal stress concept, are always related to the amount of 2 times 10⁻⁶ cycles, so which is at this point. And as you can see here, due to the amount of cycles, which is here the 2 times 10⁻⁶, and the mean value, which is at this point related to the stress ratio, you can shift your resistance curve to higher or lower stress ranges, which is just influenced by the mean value. So this is, if you go here and you say, okay, you have a mean value which is 0, then you can handle a stress range of around 80 MPa. And for example, if you go more to a tension-related behavior, so your mean value is going to tension, then your stress amount or the stress amplitude is going to be decreased. If you have, for example, a lowering of the mean value, your stress amount is going to be increased. So, which are the influences which has to be handled in the notch details? So this is the detail which is recommended in the codes, and therefore usually you have some informations due to the quality and due to the procedure, how you're gonna build your welding, for example. And so this influences also your lifetime. So some effects, and which are, you can see here, is, for example, some surfaces and internal defects. So surface defects would be like this, some changing in the cross section due to too high temperatures in the welding procedure. Then some inclusions again, which are here in the weld seam, and all these informations at the end are conducted in some categories of the weld quality. And in this weld quality, you have to go for NDT or for the shape of the structure. And at the end, in these informations, there is somehow conducted the information of defects, and also due to the shape of the weld seam, some information of the stress increasement due to the weld seam, and also some imperfections. So this is what I mean here before, is the structural imperfections on your structure, so that you have some regulations on how large can be some imperfection, which is acting on your notch detail. So again, the geometric notches, you have to think, if you go into the choosing of the right notch details. So for example, this is some specific parts which you can see here. So this is something which you're gonna never find in the recommendation of the notch details. So because the notch details always talk about some straight bars, some straight blades, and at the end, for example, if you have in your constructive design some parts where you have to decrease your structure, you have to think, okay, how you're gonna build this detail and which detail would be the best. So for example, this would be a really bad design, because you have here at this part an increasing of the stresses due to the sharp edges. For example, this part would be much more better, because you have a more smooth definition of the opening hole, and so you also get not the amount of stress increasement, and therefore the stress concentration is not as big. So also for the weld seam, this is what I meant before. You have your classification procedures, and in the classification procedure, you can see, okay, how you're going to build the weld seam and what are the parts of the weld seam. So, for example, the crack always going to cure at this part here, at this part here, or at this part here. And this is always related to the shape of the weld seam, and also due to the procedure how you're going to build the weld seam. So, for example, some more or some better quality would be also to just take off the weld seam and to make a flat bar. This could also somehow improve your quality and also give you some better resistance curve. And at this part, of course, you have here a notch failure at the K shape of the weld seam. So these notch failures can lead to a crack concurrency at this part here, but also the weld seam here has a is quite huge. So if you have here a smaller weld seam, but also which can handle the stress amount, then also the stress increasement due to the weld seam is smaller, and so some smaller the amount of cycles which you can handle gonna be increased. So, which are the influencing factors? This is something I already got somehow through in the last pages. So this is, of course, this is the strain, the stress which is loading your structure, but also the detail you're going to choose in your constructive design. So, for example, you have here some bending moment. So the bending moment also leads to a lowering stress at this part. So this part is not as much loaded, for example, as a part here. And also how you're going to apply here the structural detail. So how you're going to decide of your welding part, but also on the size of the plate you're going to add here. So, for example, a short plate always leads to a bigger amount of stress increasement. So, for example, if you use here a longer plate, then the amount of stress increasement is lower, and so also the SN curve or the cycle is going to handle there at this part going to be somehow influenced. So how does it look like if we go now for the testing and the stress dependent? So, for example, we have here our specific plate we want to investigate, and at this part we want to define a curve like this. So this is always the endurance limit, which is some horizontal part where in case of steel structures you have no fatigue damage because of the small amount of cycles, and due to the amount of cycles there also exists not as much details which have been tested, because if you're going to think about 10/8 cycles and at the end you're going to test by 4 or 5 hertz, it's going to take for one specimen 1 year. So this is something which is due to the testing procedure not really done in the last years, but it's also getting much more of interest in due to the wind turbine systems and so on. So this is the high cycle fatigue area from 10/6 or 10/7 to 10/3. And this is the most investigated part, I would say. So you have here always some different amount of cycling procedures, testing results, and at the end you're going to define a regression curve. And at the end, the highest amount of cycles you're can take there is always related to the ultimate stress in your material. So, and therefore, as I already said, you have here some different categories which are related at this part due to the cycles. So the low cycle fatigue is here related from 1 to 10/2. It can be due to some different assumptions, or materials also go to 10/2, 10/3, 10/4, 10/5. And also the high cycle amount here is defined from 10/2 to 10/7, and the endurance limit at the end is 10/7 until infinity. And this is what we're talking today is more about the high cycle fatigue area. So where we have here at this part the linear line, and we can investigate some first steps at this part. So then also some informations due to the endurance limit. The endurance limit, this is a part where I already explained before, that the endurance limit is usually a stress range where you say, okay, you have no damage on the microstructure, and so you have no damage which occurs due to fatigue and fracture. But at the end, reality is not as easy. And so we have here different lines which are defined, and these different lines are somehow, you can see here. So this would be the easiest one, is the straight line, which at the end leads to the intersection with the x-axis. Then some second one, which is mostly used in the design codes, is related to a change of the slope in your system, and the more tested part is the endurance limit, which has here the horizontal part. This part is more related to the testing procedure, why it usually occurs by sinusoidal loading. If you go more for a multiple loading, then this change of slope is more realistic and leads more to a realistic estimations. So, and what is how we're gonna do at the end our design is, as I already explained, the assumption of the minor hypothesis, and this is a linear assumption which says, okay, we have an amount of cycles. This is the amount of cycles we're gonna apply on our structure. This is the small n1. And the large n1 is the amount of cycles our resistance curve defines. So, and at the end, these cycles give some damage factor. So this can be something like 0.2. The second cycles give something like 0.3, and so on and so on. And at the end, this linear assumption has to be smaller than 0. And this is the minor rule, which is related to the linear damage hypothesis. So, and this is also something we're gonna work in the second session. And so how does it look like? The easiest assumption, the straight line. This is the basic version of the minor rule. So just or elementary rule, just to give you the words and the explanation. So the elementary form or basic rule is always the straight line. The original form of minor is the part with the horizontal line by 2 times 10/6. And the modified minor rule, which is induced by Mr. Haibach, is here with the changing of the slope. And this is more related to different load shapes and different loading assumptions. So, just to combine all informations we had here in the last 15 minutes is that usually we have here for steel structures, we have a defined resistance curve. this resistance curve has some notch details, and the notch details are always related to 2 times 10⁻⁶. So this is the green line. And due to the notch detail, which has here a resistance of 80 MPa, we also give always here the slope of the resistance curve. The slope of the resistance curve is here defined in a double logarithmic space. And therefore, we can calculate the resistance from 10⁻⁴ to 5/10⁻⁶. And from this part, we have a change of the slope with increasement of 2. And after 10/8, we have a horizontal line, which is the endurance line. And this is also the cutoff limit. So if we have, for example, stresses which are beyond this value, you can just say, okay, these values are not from important. You can skip it also in the investigation of your load investigation on your details. So, for example, if you go for an already existing structure, you can say, okay, what is the most worst case in your structure, and therefore you can define, okay, what is related to this situation, and then you can say, okay, this is some amount of cycles. If all of them are beyond the structure has endurance limit. If you are beyond above, then you have to take some assumptions on your loading, on your structure, or you have to change the design of your constructive details. So, and at the end, we talk about different areas. So the area 1 is the area with, where we have just stresses above the endurance limit. The area 2, so where we have a continuous slope. The area 2 is something where we have a change in the slope, where we have a change inside the slope. So where we have a part which are lower this point here. And the third part is something where we also have a part where the amount of cycles are beyond the endurance limit, so that we have a part of loading which we can just skip, but also a part which we have to take into account for our fatigue assessment. So how does it look like? This is a specific detail. For example, we always have in the ASHTO, or also we have in the Eurocodes, or some other regulations from companies and industries. So we have here our different SN curves. These N curves are always related to the amount of cycles here in a double logarithmic space. And at the end, for steel structures, we always talk about a slope of 3 for the high cycle area and the slope of 5 for the endurance area. And so we see here that we always have some loading which is not sinusoidal, so it is a multi-stage loading. And at the next part, we have to define our notch details. The notch detail is defined to the amount of cycles for 2 times 10⁻⁶. And so the notch detail gives here the amount of cycles you can handle. And for example, for bars, hollow sections, and plates, usually you say, okay, this can handle about 160 MPAs. So which notch cases do you have, for example? And this notch cases are always depending on the constructive details. So here you always separate on the constructive design, on the details, and you say, okay, your beam, it has stirrup, it has some welded part, it has here some attachment or something else. And so you just go through your welded beam or something else and say, okay, this part is related to the construction detail like this. And so the nominal stress concept gives you at this part the amount of cycle which can be handled at 2 times 10⁻⁶. And so, for example, for a welded seam which is longitudinal to the stresses, you can handle here 125 MPAs. For a pended blade, you can handle around 56 amount of stresses, but also, as you can see here, this amount of stress is related to the length of the appendix. So, for example, if you change the size of the appendix, also the detail will be changed. And the same for this part. So, as you can see here, for L smaller 50, you have amount of 71. For L larger 100, you have 556. So, and at the end, how do you gonna calculate the nominal stress concept, or inside the nominal stress concept? As I already said before, usually you're using some forces, for example, some automotives, some trucks, or something else. And you have therefore a specific value of the loading, and therefore you get in your beam model system, in your numerical system, you get some amount of the bending stresses, of the normal forces, and so on. And due to Bernoulli, you can also calculate here the nominal stresses, which are always rectangular, for example, to the weld seam. And but for example, in some cases, you can also, if you have, for example, here a hole, you can also take into account the increasement, or you have to take into account the increasement, and this is then a modification of the detail. So, for example, if your detail usually says, okay, you have here a hollow section, and the hollow section is without a hole, then you cannot take into account this hole in your fatigue design. So there is no sense to do an assessment due to a testing which is not related to the detail. And so you have to calculate here the stresses in the nominal stress concept. And afterwards, you also have to apply a stress concentration which is related to the hole. So you have to increase your nominal stress and then go with the increasement of the stress range into your fatigue design. Okay. So this were, it took a little bit longer. The introduction for the fatigue of the nominal stress design. So in, let's say, 50 minutes break, and then start with an example on the design of nominal stress design, and how you can calculate the equivalent stress ranges, and what are at the end the assumptions we have to consider in the design. Okay, thanks a lot.